Hello everyone, welcome back to another Math 104 lecture. So in our last video, just to recap, we finished up chapter 3.3 in the textbook, which finishes up how we handle polynomial division. So the three methods that we learned were factoring, long division, and synthetic division. We also learned a couple theorems, which were the factor theorem and the remainder theorem, and we learned that the factor theorem is essentially just a special case of the remainder theorem. So in today's lecture, what we're going to be doing is we're going to be moving on from that. We're actually getting out of chapter 3 entirely. We're now starting chapter 4. So if you're following along in the textbook, this is chapter 4.1, and what we're dealing with now are exponential functions. Exponential functions. What is an exponential function? An exponential function, which I'm going to box off in blue, is anything that's in this form. So that's where we have a function, of course, it's an exponential function, and where we have some base raised to your variable x. Now, this is different than what we've seen before. What we've seen before for like polynomial functions, for example, is we've seen, and I'm just going to write this in red, we've seen functions like f of x is equal to x squared plus yada, 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 right? Where, basically your variable was the base, and then there was an exponent being applied to your variable. An exponential function kind of switches that. An exponential function is where your variable is the exponent, and it's being applied to some number, which is your base. Okay, so a, in this case, which I have boxed in blue here, a is your base, x is your variable, that's your input to your function, right? We always know that this is your input in your function, so that's your input, and that's what's going to go right up here in the exponent. And so that's going to be applied to a, which is the base, and then c is just some coefficient. Now, a really basic exponential function is when c is equal to 1. If c is equal to 1, then c just drops out, right? And then you just have a to the x. So always be on the lookout for c being 1 and just having some number raised to an exponent, because that's still an exponential function. Okay, so there are a couple caveats to this where, in regards to your base a must be positive. So a has to be greater than 0. And also a cannot equal 1. Why can a not be 1? Well, if you think about it, if a was 1, it actually won't matter what your variable is, what your exponent is. Your input doesn't matter at all, because 1 raised to any power is still going to be 1. And then you just have 1 times whatever your coefficient is, and that's going to result in a flat line, right? That's just going to be a number. For example, if we had, and I should write this in red, if we had f of x is equal to, let's say, 3 times 1 to the x, well, once again, it doesn't matter what x is, because 1 to the x just simplifies down to just be 1, regardless of what the exponent is, right? Even if the exponent is 0, 1 to the 0 is still just 1. So you would just have 3 times 1, which is 3, and f of x is equal to 3. Well, we know that this is just going to be a horizontal line, right? It doesn't matter what input you have for x. Your inputs for x can always be changing. Your output is always going to be 3, so this is a horizontal line, so this is not an example of an exponential function. Okay, so just remember these two rules here for your base. Your base has to be positive, and your base also has to be not equal to 1. Okay, but short of that, your base can be any other number. We're going to see in just a second here that your base can actually be a fraction. Okay, so the domain of an exponential function, and I'm just going to abbreviate this, the domain of an exponential function, just like polynomial functions, is all real numbers. You can plug in any number for x, and that's still going to be an exponential function. Even if x is negative, it's still going to be an exponential function, and we'll take a look at that in just a second. So let's just get this out of the way. So we know that the domain is all real numbers, and the way that you say that is from negative infinity to positive infinity. Okay, so let's work through a couple examples here just to really fully understand what we're doing. Let's let, and I'm just going to get rid of this example, but we'll keep the box up here just so we know what we're doing. Let's let f of x equal 1/4 to the x. Okay, so our base is a fraction. Our base is 1/4, and our input, again, our variable is x, right? So that's going to be how we know that this is an exponential function, because our input is now an exponent. Okay, so what I want to do is I want to find f of 2 and f of negative 3 halves. Let's work with f of 2 first. What does this mean? To find f of 2, 2 is now my input. What that means is I'm plugging 2 into my function f. So wherever there is an x, I am now plugging 2 in. And that means that I'm going to have 1/4 raised to, because again, this was raised to the x, now this is raised to the 2. So this is 1/4 squared. And what is 1/4 squared? Well, the way that you handle fractions raised to an exponent is your exponent gets applied to the numerator and to the denominator, right? So that means you have 1 squared over 4 squared, and 1 squared is 1, 4 squared is 16, so you have 1 over 16. So we've just shown that f of 2 is 1/16. Okay, and now to do f of negative 3 halves, well, this is where I hope you guys remember your exponent rules, okay? Because you're going to need your exponent rules from going back several lectures to be able to understand what's going on with exponential functions. So this is again some good practice here. So f of negative 3 halves, what does that tell us? Again, that tells us we're plugging in negative 3 halves into our x. So we're starting with our base, which is 1/4, and we're plugging in to the negative 3 halves for our exponent. Let's break this down one piece at a time. What does this tell us? Well, let's handle the negative sign first. Remember what a negative sign in your exponent does. It implies a fraction, right? And it flips it on its head. So if you already have a fraction, all you're doing is you're flipping that fraction where the denominator becomes the numerator and the numerator becomes the denominator. So I'm going to just get rid of that negative and do the simplification, and we would have 4/1 to the 3 halves. And you should agree with me, 4/1 is just the same thing as 4, so I'm just going to make this 4 to the 3 halves. Okay, well, great. We have 4 to the 3 halves. How do we handle this? Well, that is essentially, if you guys remember, a rational exponent. What that means is we have 4 raised to the 3rd power, and also the square root of it, right? Your denominator of the exponent tells you the index of the root, and the numerator of your exponent tells you what you're raising the base to. So we're raising our base of 4 to the 3rd power, and we're also taking the square root of it. I like to go in the opposite order, because I like to reduce first and then make the number bigger, so that way I'm not getting a really large number and then going downwards. But either way, we know that this should come out to be the same. So what I'm going to do first is I'm actually going to take the square root of 4 first and then do the cube. And we already talked about this, how this is still equal regardless in the order that you do this. And we know that when we take the square root of 4, we're not solving for a variable. We're only talking about the principal root, so we're only talking about positive 2 here. So that's 2 cubed, and 2 cubed is 8. And once again, if you did it the other way, where you did the 4 cubed first, 4 cubed is 64, and then you would have the square root of 64, which is, once again, 8, giving you the same answer either way. Okay, so hopefully that's some good practice, kind of shaking the rust off for your exponent rules. If you don't remember that, go back to the lecture video where we covered it, and hopefully this would make more sense. Again, what I did first was I just took care of the negative in my exponent, so that piece right there. The negative implies that I flip the fraction. So if I had 1/4, it becomes 4/1. Conversely, if I started, hypothetically, with 4 to the negative 3 halves, then that negative would make it 1/4 if I started with 4. Okay, so the negative means that I flipped it on its head, and then now we just take care of the 3 halves, and the exponent of 3 halves tells me I'm raising my base to the 3rd power, and I'm taking the square root. Okay, and then we, of course, like I just said, know we can do this in any order that we want. Okay, so now that we've done that, let's talk about some facts of exponential functions. These are things that are universal for exponential functions as long as they are in a particular form. So let me just erase all this and we'll look at these 5 facts that you should know. Okay, so first off, assume that you have an exponential function, f of x, and we're not dealing with any sort of coefficient. Okay, so this is just a basic exponential function. Your coefficient is just 1, right? Your coefficient, which we just talked about, c is equal to 1, so it's just going to drop out here, and you just have f of x is equal to a to the x. Okay, and once again, we have this caveat, which I'm just going to underline in red. Your base has to be positive, and your base cannot be 1, because otherwise you would just get a horizontal line if it were equal to 1. So with those being said, we already talked about the first thing, which is your domain. Your domain of an exponential function is always going to be all real numbers. You can plug in any number for x, and it's going to be defined for that number. Your range, as long as you don't have any sort of coefficient, as long as you don't have anything added to a to the x or subtracted from a to the x, your range is always going to be, again, and I'm just going to box this in red because this is very important, as long as it's in that particular form, your range will always be from 0 to positive infinity, not including 0. What does that mean? Again, range is where we're talking about reading from bottom to top, right? We're talking about our outputs. So what this tells you about exponential functions that are in this form is that your exponential function never actually touches the x-axis. It never touches 0 for y. If it touches 0, then that means that there had to have been some other manipulation going on where a to the x was being added to something or subtracted from something, or something else is going on. Okay, so your domain is all real numbers. Your range is from 0 to positive infinity. So your range is always just going upwards. Okay, all right. Next up, your graph, as long as you have this exponential in the function in this form, your graph is always going to go through 3 particular points. Regardless of what your graph is, regardless of what your base is, I should say, that, a could be 7, it could be a billion, it doesn't matter. It's always going to go through these particular 3 points. -1, 1 over a. So essentially what that means is if your base was 7, then it would go through -1, 1 over 7. So -1 and 1/7 as your y value. It's always going to go through the point 0, 1. And finally, it's always going to go through the point 1, comma, and again, whatever your base is. So if your base was 7, then in this case, it would go through 1, 7. Okay, so those 3 points guaranteed every time. You know those 3 points are going to exist on your graph as long as your function is in the form boxed in red. The third thing is we have a term that I don't believe we've encountered in this class before, so I will try my best to walk us through this if you've never heard of this term before. So the third fact about exponential functions here is that the x-axis is the horizontal asymptote. What is an asymptote? If you think about graphs like a field for any kind of sports, whether it's tennis, football, soccer, you always have some sort of out of bounds, right? You always have a line that marks things that that are okay to be played in, and then once you cross that line, well, basically, you're not allowed to cross that line, right? The ball is never allowed to cross that line because then it would be illegal, right? That's the entire idea of the field of play. So if we're talking about asymptotes, when it comes to mathematics, an asymptote is basically a line, and in this case, it's a horizontal line. So it is the horizontal line that prevents the graph from going any further downward. So this should actually make sense when we're talking about the range. So the first fact in regards to the range and the third fact kind of go hand in hand. The reason is because, again, if you think about your range, we're talking about it being always greater than 0, right? If I'm just going to draw this real quick, we're talking about numbers that are always going to be bigger than 0, right? This is not a graph of an exponential function, just for the record. I'm just drawing a function that has a range of, larger from 0 to infinity. So notice in this case that, well, it never actually touches 0. We can get very, very, very close to 0, but it'll actually just keep getting infinitely closer to 0 without ever touching it. And that's how you know that your x-axis is your horizontal asymptote. Notice that, again, if you're considering this like the field of play, it's never crossing that boundary, right? It's always keeping the ball or the function in the bounds of play. So you're never going to get an exponential function, as long as it's in the form boxed in red, you're never going to have the graph of an exponential function dip below the x-axis or even cross the x-axis. It'll never hit it. Okay, it'll get very, very, very close infinitely close, in fact, but it will never actually touch the x-axis. And that's what an asymptote is. It's a line that your function gets very, very, very close to, but it will never actually touch. Okay, so if you have questions about that terminology, feel free to let me know, and I'll try to go through a more rigorous definition of that, but hopefully that makes sense to you just, from me reading it. Okay, so the fourth fact here is that if you have another exponential function where you have the same base and the only difference is that your exponent is negated, then that is going to be the y-axis reflection of your first function. So again, your first function is f of x is equal to a to the x. If you have, again, the same base, so the same base, still a for your g of x, and we just have that negation, it's going to be a y-axis reflection. And last but not least, and this is the one that we'll probably have to show, and we will show this in just a second, is that it's not going to be that intuitive, but we'll read through it anyway. Assuming you have two numbers where you have a and b and they're both positive, you have a function that's an exponential function g of x such that it's noted by b to the x, so your larger number. And then you have another function, f of x, where you have your lesser number, a to the x. Well, a to the x will lie below the graph of g of x when you're talking about when you're talking about from 0 to infinity. So we're talking about the x inputs from 0 to infinity. And it's going to lie above g of x from negative infinity to 0. Again, I'm 100% sure that made no sense, just from reading it. And that's why we'll actually look at an example of this in just a second here. Okay, but just take that fact for what it is. That is a fact about exponential functions that are in this form. As long as you understand the first four, you're good to go. And then the fifth one will make more sense when I show you an example. Okay, I'm going to go ahead and clear this off, and we're going to move on here. So your first classwork example here is I'm going to give you two functions, and the functions I'm going to give you are f of x. Actually, you know what? Sorry, I just realized I do not want to clear off all these facts. Okay, so your first function is f of x is equal to 1/2 to the x, and your second exponential function is g of x is equal to 2 to the x. So given the following x inputs, and the x inputs are x is equal from -2 to 2, only talking about the integers. So x is equal to, we don't even need that. So -2, -1, 0, 1, and 2. What I want you guys to do for your first classwork assignment is just make a table of values. So what that means is just, you have your x column. These are your x inputs. Once again, -2, -1, 0. Come on, buddy, scroll. There you go. 1 and 2. And then what I want you to do is figure out what f of x and g of x are for each of these inputs. And then after you do that, what we're going to do is we're going to try to sketch this, and we're going to compare these two graphs to each other and see what we can determine, based off of these and the facts that we wrote above. So just figure out, what happens when you plug in -2, -1, 0, so on and so forth into the following functions. Okay? All right, I'll give you guys a couple seconds to do that. Okay, so again, what we're doing is we're taking -2 and we're plugging that in as our input, right? Our input is x. We know that our x is -2. So in this case, we're plugging -2 into f, which means, and I will do it over here, if we have f of -2, that means we have 1/2 to the -2 power. Well, deal with the negative first, just like I did earlier, right? What does dealing with the negative first mean for our exponent? That means taking our fraction and flipping it around. So we have, instead of 1/2, we'll now have 2/1, which just simplifies down to just be 2, right? 2 divided by 1 is just 2. So now we have 2, and we dealt with the negative, so now it's just 2 squared. And 2 squared is equal to 4. So we know that when we have -2 plugged into f, we get a positive 4. Okay, let's plug -2 into g of x and see what we get there. So now we have g of -2. And when we do that, g of -2, well, that is 2 to the -2 power. Once again, handle the negative sign first. That we know 2 is the same thing as 2 over 1, so we're flipping that on its head. So we have 1/2 squared. And when we square 1/2, we know that we square the top, we square the bottom. So that's 1 squared over 2 squared, which is just 1 over 4. So we get 1/4 here. Okay. -1 now. So if we have f of -1, that means we're going to have 1/2 to the -1. 1/2 to the -1, well, that's really easy, right? All we're doing is we're just applying our negative, right? We're taking care of the negative sign here. So we just flip it on its head. So we have 2 to the first power, and 2 to the first power is just 2. So we get a 2 over here. I'm actually going to finish the F column first, and then I'm going to finish the G column. I don't know why I was flipping back and forth, making my life more difficult than I need to. So f of 0, well, we know that any number to the 0 is just equal to 1. That's one of our exponent rules. It doesn't matter what our base is, as long as our base is not 0. We can't have 0 to the 0. I already discussed this going way, way, way back in the very first lecture. We're not going to examine 0 to the 0 in this class. That is an undefined thing, although we mathematicians, we generally assign it the value of 1 because the limit approaches 1. But that's for a pre-calc or calculus class. So don't worry about 0 to the 0. But for all other numbers, as long as your base is not 0, any number to the 0 power is equal to 1. So 1/2 to the 0 is just 1. And then we have 1/2 to the first power. And any number to the first power is just that number back. So we just get 1/2. And last but not least, we have f of 2. And f of 2 means we have 1/2 squared, and we already talked about what we do with this. We square the top and bottom, so we get 1/4, right? So we end up with 1/4. Okay, I'm going to go ahead and erase some of my work just so I can, again, just keep everything pretty neat and close to my chart here. Okay, so now we have to figure out the G column. So figuring out the G column together, we have to do G of -1. Well, G is 2 to the -1. And what that does is that just flips it on its head, right? So we have 1/2 because that's 2 over 1 raised to the -1 power. So it's 1 over 2 to the first power, which is just 1/2. So we get a 1/2 right here. Then we have G of 1. G of 1 is 2 to the first power, which is just 2. Any number to the first power is in fact just, oh, I'm sorry, that was not G of 1. My mistake. Well, that would be right here. G of 0 is the one that I missed. G of 0 is 2 to the 0 power, which is 1. Again, any number to the 0 power is 1. And last but not least, we have G of, I don't want to mess up here, G of 2. So we have G of 2, and that is 2 to the second power, which is 2 squared, which gives you 4. Okay, we have now completed our chart here. Why did I want to do this? Again, the entire idea that I wanted to do here is I wanted to graph this, right? I wanted to plot this out onto a graph so we can see exactly what's going on. Now, for the sake of argument here, if my laptop would stop lagging, that would be even better. What I want to do is I'm going to plot my f of x. So this column here, I'm going to plot in red, and then my g of x, I'm going to plot in green, and I'm going to plot them both on my graph at the same time, just so we can really understand what's going on. So bear with me for 1 second while I break out the ruler here and get this going. Okay, so we're going to have 90 degrees. Fantastic. Okay, so we broke the ruler out. We got the nice lines. Fantastic. This is our x-axis. This is our y-axis. Okay, now let's go ahead and start plotting some numbers down, right? Let's say that up here, let's do, this is 1, 2, 3, 4, and let's just say that's 5, even though we don't need the 5. And then for our x-axis, let's say this is 1, 2, 3. And down here, this is -1, -2, -3. Okay, let's go ahead and plot f of x first. And again, I'm going to plot this in red. So f of x, again, our first input is -2 and our output is 4, right? That's the whole point of functional notation. We have some input, we get some output. So we have -2 and -2 plots to 4. So we are right about here. Sounds about right. So that's our first point. Okay, next up, we have -1, 2. So that's going to be right about here. And then we have 0, 1. So 0, 1 is going to be right there. We have 1 and 1/2. So 1 and then 1/2 is approximately going to be right here. Don't hate me for not being super accurate. And then last but not least, we have 2 and 1/4. So our input is 2 and our output is 1/4. So again, bear with me, but that should be fairly accurate right there. Okay, and when I try to, emphasis on try, when I try to graph this, it's going to look like some kind of curve here. So our curve is going to look something like, that was miserable. Let me try that again. There we go, much better. Okay, so we go like that, right? Okay, before we start talking about f of x and what this means, and especially in regards to the facts that we were talking about above, let's first plot g of x. So g of x here, again, our first input is -2 and 1/4. So -2 and 1/4. Actually, we're going to come back to that just because I want to keep it. I'm going to go from bottom to top for this one. So we have 2, 4. So 2, 4, we're going to be over here. So this is our first input. Then we have 1, 2. So 1, 2 is going to be right here. Next up, we're going to have 0, 1. So notice we get the same point here. So I'm just going to put little green dot in the middle of it. But we know that 0, 1 is also going to be a point that we have in common with f of x. And then we have -1/2. So -1/2 is going to be right about here. And last but not least, the one that I was going to start with, -2 and 1/4, that's going to be approximately right about here. Okay, let's go ahead and graph this and see what's actually going on here. So this is going to look something like that. And again, if you want a more accurate picture, please feel free to visit any sort of graphing online software that is going to do this better, or any kind of graphing calculator, but this is a decent representation of what's going on. Okay, so why did I do this? What's the whole point of this? Well, first off, this gives you a good idea of what an exponential function looks like and what it's doing. When we're talking about g of x, notice that our base is bigger than 1, right? Our base is 2. When your base is larger than 1, your exponential function is going to start slow. So it's going to start, negative, and then it's going to rise, and it's going to rise exponentially positive. So notice that we started from, negative numbers. Well, we started from 0 essentially for our range. Notice how it's never actually touching 0. It just gets very, very, very close to 0. And then it goes up towards infinity, right? Okay, so the idea is that this is an increasing function, right? We talked about increasing and decreasing before. When your base is larger than 1, your exponential function is increasing. Okay, and now when we're talking about f of x, again, our base is 1/2, our base is less than 1, our exponential function is decreasing, right? We are starting from essentially infinity, and we're going down up until we get very, very, very close to 0, right? So we are decreasing that way. So the idea here is that, again, your base determines if you're increasing or decreasing, depending on if it's less than 0 or greater than 0. What other things can we draw here? Well, we can draw from the fact that we know that, again, our range is 0 to infinity, right? And when we talk about range, we're always reading from the bottom to top. Notice it gets very, very, very close to 0. Both of them do, but neither of them actually ever hit the x-axis, which means neither of them ever actually hit y is equal to 0. So your range can't equal 0 at any point. So it starts from 0, not including 0, but goes up towards infinity. It goes up forever. And again, the one that was related to it, number 3 here, the x-axis is the horizontal asymptote. Well, notice neither of these functions ever cross the x-axis. They get very close to that line. Your x-axis is the line here that they get close to, but they never actually ever touch it. They just get infinitely closer and closer to it without ever actually touching it. And last but not least here, what I wanted to discuss is number 4, which is this whole y-axis reflection thing. So what did the y-axis reflection depend on? It depended on having the same base, but a negative version of the exponent, right? Well, when we're looking at our two functions, it doesn't immediately appear clear that we have the same base. But in reality, we actually do. So the reason we actually do is because we know that 1/2, sorry, 1/2 is really 2 to the negative 1, right? So if we're talking about f of x being, 1/2 to the x power, g of x can always be remanipulated here to be, well, this is going to be the same thing as 1/2 to the negative x power. Right? If you were to go backwards, if we were to go in this direction and take care of that negative sign, what would that negative do? The negative would flip the fraction on its head, so that 1/2 would be 2 over 1, and then, well, your negative sign would go away, and you would just have your, your regular exponent, right? So it would be 2 over 1 to the x, which is just simplifies to be 2 to the x, which is what we started with, right? So, and of course, we can do the same thing. I'm just going to erase this real quick. We can do the same thing for f of x. We can say that this is, in reality, 2 to the negative x, right? Because what is this telling you? If you were to go in this direction, if we were to go backwards, what would that negative do? Well, that negative would take your 2 over 1 and make it 1 over 2. And then you would just have your positive exponent x. So in reality, notice, I should just leave this, sorry. Notice how, if we're talking about this group right here, which I'll circle in red, or this group right here, which I'll circle in blue, it doesn't matter how you want to reshape this. We can always see that they are, in fact, the same base with just negative exponents of each other. They just have, different flipped signs of the exponent. So as a result, we know from our fourth fact that they should be y-axis reflected of each other. And in fact, they are y-axis reflected of each other. Notice how they, if we were to talk about the y-axis as the line here, they absolutely reflect over that line and would be, the other function here. Okay, so notice how all of these facts are coming into play. So try to understand them as best as you can. And our domain, the only piece that I didn't talk about from the first 4 facts here is the domain being from negative infinity to infinity. And notice how it doesn't matter what x input you plug in, because they go on infinitely for your y output. You can plug in any x input, which means your domain is all real numbers. And also, I forgot to mention, and this is my mistake, the second fact here, which is the points that it's going through. Well, we can verify all of these points. So the easiest one to verify is the 0, 1. Well, when we did our charts here, notice how they both went through 0, 1, right? For f of x, your input was 0, your output was 1. For g of x, your input was 0, and your output was also still 1. That's how we got this point right here, 0, 1. So it doesn't matter what your base is, your base will always go through that, or I'm sorry, your function will always go through the point 0, 1, as long as it's in the form f of x is equal to a to the x. And then the other points that it goes through are -1 over, -1 comma 1 over a. Well, our a in the case of g of x was 2, right? So we should have -1 and 1 over 2 as our output. And in fact, we have -1 and 1 over 2. And for f of x, we should have -1 and 1 over 1/2, which simplifies to be -1 and 2. And what I mean by that, if we had the point, we're talking about the point -1, 1 over a. For f of x, this is -1, 1 all over 1/2. And I'll leave this simplification for you. It's a complex fraction. It's not that bad to deal with. And again, we know that this is -1, 2. Okay, so we see that we're getting that point regardless what your base is. And the last point is 1 comma a. So 1 is your input, and a is your output, and a in the case of f of x was 1/2, and a in the case of g of x was 2. So notice that we're getting those points regardless what your base is. It doesn't matter what your a is, you're always going to get those 3 points on your exponential function graph. Okay? Okay, let's go ahead and clear this off here finally. All right, so let's get to some actual mathematics here instead of just graphing. So what I want to do is, in this example, I want to find the exponential function. So I want to find an exponential function in the form f of x is equal to c times a to the x. So we might have a coefficient here. And what we're given is, so I want to find the, function in the form of f of x is equal to c times a to the x if f of 0 is equal to 1 and f of 2 is equal to 49. Okay, so how do we approach this? Well, what we have to realize is what is unknown here. I want to find a function in this form, right? So what are my two unknowns? Well, I have to figure out what c is, and I have to figure out what a is. We don't have to figure out what x is because, well, in a function, x is always going to be your variable, right? X is your input. So you're not trying to figure out what x is. You're trying to find the function given these two pieces here, given these two pieces of information. So what I'm going to do first here is I'm going to use my f of 0 is equal to 1. And I'll explain why I'm going to use that first in a second here. But if you decide you wanted to use f of 2 is equal to 49 first as your first piece of information, that's not incorrect, and I'll show you why shortly. Okay, so if we start with, okay, well, I know I will need to get in the form f of x is equal to c times a to the x. And what do we know? Well, we know, again, I'm looking at the piece here, which I'm boxing in green. This is my first piece of information that I was given. F of 0 is equal to 1. That means that 0 is my input, which means 0 is my x value. And 1 is my output, which means 1 is this entire piece here, which I just underlined in green. Okay, so that means I can reduce this to be 1 is equal to c times a to the 0. And the reason that I picked this piece as my first piece of information is because notice how easy it is to solve for c now. A to the 0 is just going to cross out to be 1, right? It doesn't matter what a is. Any number to the 0 power is just going to be 1. So we just have 1 is equal to c times 1, which means 1 is equal to c. So yeah, we just figured out what c is. Because again, we were able to solve for, we were able to cross out a. Just with the information that we were given. So, okay, one piece of information, we're good to go, right? If we're talking about C and A, we found that C is equal to 1. That one's done. We still need to figure out what A is, right? But now we know what C is. So that's going to help us out. So what we're going to do now is we're going to use the other piece of information, and we're going to set this up one more time. So f of x is equal to c times a to the x. Again, we know that it has to be in this form. That's what we're looking for. And now we're going to use the other piece of information. So 49 is my output, and 2 is my input. So what that means is 2 is going to be my x, 49 is going to be my total output. So I have a squared, and what was c? Well, c was just 1, right? Which means that the 1 is just going to go away, right? 1 times any number is just that number. So we have 49 is equal to a squared. And now what do? Well, we just solve for a, right? So we take the square root of both sides, and we get a is equal to plus or minus 7. Now, here's the thing. I know for a fact I only want the positive value, a is equal to 7. The reason that I know this is by the definition of an exponential function. Remember that when I first brought up exponential functions in this form, f of x is equal to c times a to the x, we had that little caveat where a has to be greater than 0 and also a cannot be 1, right? So we know we can cross out the -7 because by definition of the exponential function, a has to be positive. Okay, so we can get rid of the negative value here, and we know then that a is equal to 7. So hooray, we have now figured out c is equal to 1, a is equal to 7. So if that's the case, we can finally write our function as f of x is equal to c times a to the x, but we know c and we know a, so f of x is equal to 1 times 7 to the x, which just simplifies to be f of x is equal to 7 to the x. And we're done. This is your final answer. So you have now figured out your function based off of the two pieces of information that they gave you. Why did you need two pieces of information? Well, it's because you had two unknowns. You needed to find c, which, where is it? There we go. You needed to find c, and you also needed to find a. So you would only be able to find out one of those if you were given one piece of information. But because you were given two pieces of information, then you can find both. Okay, so for your second classwork assignment, what I want you to do is actually, sorry, before I jump the gun, let me go ahead and illustrate why you can do the other, why you can start with the other piece of information first. So the two pieces of information, once again, I know I just cleared it, but we were given f of 0 is equal to 1 and f of 2 is equal to 49. Okay, if you went about it the other way where you used this piece first, that's totally acceptable. It's just a slightly more annoying way to go about it. So if you have f of x is equal to c times a to the x, and what you're going to do now is you're going to use this piece of information and you're going to plug in, right? So, okay, plugging in, that means that I have 49, right? Remember, 49 is your output, so that's going to be your output. So you have 49 is equal to c times a squared, right? Now, here's where things get a little bit tricky. You haven't actually solved for, you haven't gotten rid of one of your variables, right? You still have one variable, two variables. So what you should do here is if you can't cancel out one of the variables immediately, if basically what I'm saying is if your input is never 0, because 0 is the only way that you're going to cancel a to the x, then what you should do is solve for one of your variables. So what do I mean by that? I mean, okay, well, let me solve for c, and then I'll go back and figure out what c is later. So solving for c, that means I'm going to divide both sides by a squared. So I'm left with c is equal to 49 over a squared. Okay, cool. I don't necessarily have an exact value for c, but at least I have something that I can plug in now, right? So I have 49 over a squared. Cool, that's fine. So now going back, setting this up one more time, f of x is equal to c times a to the x. And now we're going to use the other piece of information. Now we're going in the opposite order. We're doing, the f of 0 is equal to 1. Well, that means we have 1 here. We have c, but what is c? C, we just figured out, is 49 over a squared, right? So that means we have 49 over a squared times, well, a, and then what was my input? My input was 0, right? So 49 over a squared times a to the 0. Well, this becomes 1 is equal to 49 over a squared times 1, which we can just get rid of that times 1. Now I'm going to move that a squared over to, I'm just going to multiply both sides by a squared. So I have a squared is equal to 49. And now we can finally get an answer for a. And to get an answer for a, we take the square root of both sides. And taking the square root of both sides, we get a is equal to plus or minus 7 once again. And once again, we know that we're just talking about a is equal to positive 7 here. And now that you have an exact number for a, you can now take this number for a and plug it back in and figure out what c is, right? So c is equal to 49 over a squared, which is 7 squared. And that's 49 over 49, which is equal to 1. So either way, regardless how you did it, you can get the same answers. C is equal to 1 and A is equal to positive 7. It doesn't matter what order you do it. It's just that if you do it in this order, where things don't cancel out immediately, solve for one particular variable. Put one variable on the other side so that way you can solve for it later. Okay, and I think you have a couple homework questions that are like that. So, that's okay to do. You can absolutely solve for one variable and have your other variable on the other side. It just means that you're going to be solving for C later on. Okay, all right. So what I want you guys to do is do the next classwork example. So the next classwork example is, once again, find a function in this form. F of x is equal to c times a to the x. And the given information that I'm giving you is f of 0 is equal to 3 and f of 2 is equal to 75. So give it a shot, see what you come up with, and feel free to unpause the video whenever you are ready. Okay, so let's do this together. So I'm going to do this again. I'm setting this up. I know that I need it to be in this form, right? F of x is equal to c times a to the x. That's, the form I'm trying to get here, right? So what I'm going to do is I'm going to be plugging in from my given material. And once again, I'm going to start with this one here because this would simplify matters immediately. As I just showed, if you wanted to, you could do this one first, and that's absolutely an acceptable way to go about it. It's just going to take you a little bit longer because there's a couple other extra steps you have to go through. So with this tells me my output is 3 and my input is 0, right? So I have c times a to the 0. And a to the 0 just is 1, right? That's just going to cancel out. So I have c times 1, which is just c. So hooray, I have now figured out c is equal to 3. Okay, cool. I'm half done already. I figured out what one of my variables is. I just need to figure out the other variable, which is a. So now we come over here and we set this up again. F of x is equal to c times a to the x. We use our other piece of information here. So my output is 75 and my input is 2. But this time we know what c is, right? C is 3. So we have 3 times a squared, right? My input is 2, which means my x is 2. So I'm raising a to the second power. Okay, so now I just need to solve for a. So solving for a, what I'm going to do is I'm going to divide both sides by 3. So divide by 3. Divide by 3. And what happens here? 75 divided by 3 is 25. 3 times a squared divided by 3. Well, 3's are just going to cancel out, which is what we wanted. So that way we can isolate a. So we have 25 is equal to a squared. And we do the same thing, right? We square root both sides. We know we're going to get a plus or minus here for this. So we get plus or minus 5 is equal to a. But once again, we can get rid of the minus because we know a has to be positive. Our base always has to be positive here. So we get a is equal to 5. And hence we can write our final equation as f of x is equal to 3 times 5 to the x. Okay, please, I just remembered, please do not make the mistake of thinking you can multiply the numbers together. You cannot, you 100% cannot do this. You cannot multiply the 3 and the 5 together. Why can't you? Well, you can't because they are raised to different exponents, right? This, your 3 is raised to the first power. Your 5 is raised to some power, which you don't know. You don't know what that power is. It's raised to some x, right? If you multiplied your 3 times the 5 to get 15 to the x, what you're essentially saying is, okay, well, I'm also raising my 3 to the x power as well. And that's not the case, right? 3 is your coefficient, so it's always to the first power. So please do not multiply your coefficient times your base. Keep them separate. It's 3 times 5 to the x, okay? And if it helps you remember, draw parentheses, right? Put parentheses around the coefficient or put parentheses around the exponent, however is going to help you remember. Just make sure you don't multiply the coefficient and the base together. Okay, so this here, f of x is equal to 3 times 5 to the x is your final answer. And once again, we found that the same exact way, right? We set it up. F of x is equal to c times a to the x, which means, that was the form that the question wanted us to find the function in. So then we just used our given materials. We solved for c first. Once we knew one of the variables, we then solved for the other variable, right? We knew what c was, so then we had the necessary information to then solve for a. And once we had c and a, we can then get the equation. Okay, so let's see, how long have I been talking for? 49 minutes. Okay, we'll keep going a little bit longer here, not too much longer. Okay, so the next topic that we're going to talk about here is interest. interest. Hopefully you're interested. So the idea here is there's a couple different forms of interest. The three forms of interest are simple interest, compound interest, and continuous compound interest. That word continuous is very, very important. I'm not sure if we're going to get to it today, probably not, but the idea of compound interest and continuous compound interest being different is something that you need to remember, okay? So let's start with the basic one, and the basic form of interest is just simple interest, okay? So I'm going to write simple interest. Okay, simple interest. Basically, what's happening here is your interest is only on the principal amount. If you guys are not business majors and you don't know what principal amount means, that principal amount is always your initial amount that you're investing. So if we're talking about interest here, it always helps to talk about money because interest and money kind of go hand in hand, especially in today's modern world. So think about money here when as we go through the rest of this topic. So when I say that your interest is only on your principal amount, I'm saying your interest is solely on the amount that you start with, and that's it. You're not getting compound interest. You're not basically accruing more and more as you get more. You're basically only accruing interest on the amount that you put in. So how do we write this out? We write this out as I is equal to PRT, and also I'll explain what all of these variables mean shortly. And also A is equal to P plus I. Okay, so notice here, I shows up twice, right? You have I coming right over here. So if you wanted to, you could kind of put this together and lump this as one equation. A is equal to P plus PRT, right? Where I'm just basically taking my I, which is equal to PRT, and plugging it in right in there, right? So what's actually happening here? What does all of this mean? Okay, let me write out all of the variables. I is your interest. I misspelled interest. Wow, how embarrassing. Interest. There we go. Okay, so I is your interest. P is your principal amount, or you can think about it as your initial investment, your initial amount of money that you're putting in, okay? R is going to be your interest rate. So whenever you put money in, like into a bank or into a savings account, you're always going to have some sort of interest rate on that account, or on, the investment that you're putting in. Again, assuming you put your money into a bank, some people don't trust banks. That's okay. So R is equal to the interest rate. And then finally, T is the number of years. So T is going to be number of years. And in general, we do, when we're talking about interest, we do talk about T in terms of years. So if somebody quotes you, a certain number of months, you have to convert that number of months to years. If somebody says, okay, this will be invested for 18 months, you can't put T is equal to 18. You have to convert months to years. So 18 months is the same thing as 1 year and 6 months. 6 months is, half of a year. So you have 1.5 years. Okay, so just keep in mind that we are talking about T in terms of years. Your time is in terms of years here. And last but not least here, A is your total. So this should make sense here. And I'm actually going to erase this piece because I just want to talk about it in two separate pieces. So your interest, which I'm just going to highlight here in red, your interest is defined by, when it's simple interest, it's defined by the amount that you're putting in times your interest rate times the amount of years that it's gone for. Okay, and then your total amount is however much you put in. So your total amount, which I'm highlighting in green here for money, right, is the amount that you started with, which is your P, your initial investment, and also however much interest you got on your investment, right? So that would be your total accrual. Okay, let's do an example of this so that way it doesn't just feel like, I'm waving my hands in the air here and talking at nothing. Okay, so let's say my initial investment that I'm putting into a bank is $100, and I have an interest rate of 4% over 6 years. what would the total be at the end of the 6-year period? So I'm going to read that again, and this time I'm going to write it down. So again, my initial investment, if the initial amount is $100 with an interest rate, God, my handwriting gets like, it just deteriorates as the video goes on, with an interest rate of 4% over 6 years, what would the total be? Okay, so what's my idea here? The idea is first we have to figure out how much interest we got. Before we can figure out the total, again, your total is the amount that you started with and then your interest. But if we don't know what our interest is, we can't figure out what our total is, right? We have the amount that we started with, right? The amount that we started with is $100, but we don't know our interest yet. So let's figure out the interest and then we can figure out the total. So again, our equation for interest is I is equal to P times R times T. Your interest for simple interest is determined by the amount that you put in times your interest rate times the amount of years that it's gone for. So plugging everything in here, we have 100 times, and hopefully you guys know how to convert percents to decimals, but if you don't, 4% is the same thing as 0.04. This is percentage is always based out of 100. So if you have 4, that's 4 over 100. Okay, so 4% is 4 divided by 100, which is, and of course, if you wanted to, you can always write it as a fraction, which is 4 over 100. But 0.04 also works, however you want to write it. I'll keep it as a fraction just because I know that over the course of this semester, I've said, please put fractions. So we have 4 100ths, and last but not least, time is 6 years here, right? So times 6. What's going to happen? Well, lucky for us, 100 and 100 cancel out. That makes our life easy, right? And then we just have 4 times 6, which gives us 24. And now to figure out the total, all you're doing is you take your interest and you add it to the amount that you started with, right? So A, which is your total, is equal to P, which is the amount that you started with, plus I, which is your interest. So your total is equal to 100 plus 24, which is 124. So that's it. That's simple interest. Okay. The idea behind simple interest is that you're just, getting money off of the starting money that you put in. Now, there's something that I want you to notice here. What I want you to notice is that this is a linear equation. How do you know this is a linear equation? Everything here is to the first power. There's no exponents going on. There's no exponential functions going on here, right? This is a linear equation, so the amount of money that you get is linear. And if we're comparing a line to, say, an exponential function, again, let's do something like this. A line is always going to be steady, right? I can't tell you what the equation of this line is, but just to give you an example, a line is always going to be steady. It's going to give you, a steady amount of money back each and every time, right? But an exponential function, well, an exponential function, we know that it always is going to start at the point 0, 1 here, right? An exponential function is going to look something like this. It's going to look unsteady for a while, and then it's going to shoot up. And it's just going to keep on going, and it's going to shoot up really, really, really fast as time goes on, right? And we're going to start to see that with other forms of interest. So that's simple interest. And again, simple interest really isn't that bad. It's just remembering the formulas. I is equal to PRT, and then your total is just the amount that you invested plus the interest that you got on the investment. Okay, so that's that. Okay, so let's talk about one more version of interest here, and then we'll call it a day here, and we'll do the one last classwork example. So what I want to talk about now is compound interest. So compound interest. Okay, so compound interest. The idea behind compound interest is that your interest is accrued on the original amount, just like simple interest. However, it's also accrued on the interest of the previous years. So that means as you get more money, it adds your interest to the total, and then you get interest on that larger total for the next year, or however many times it accrues in that year. Okay, so basically, it's not doing what simple interest did. Simple interest, it just, you got your interest one time, right? It hit, if you plugged 100 in, you got your interest on 100, and then you got your total, and that was it. For compound interest, it's doing that, but a bunch of times over. So in theory, you should get a larger number back from compound interest. So let's take a look and see what's happening here. Okay, once again, we need a formula for compound interest. So let's define a formula. We have A is equal to P times 1 plus, and it gets a little messy here, so feel free to pause the video if you need to. So we have A is equal to P times 1 plus R over N to the NT. So this piece here that I just underlined, that's an exponent, so to the NT. So once again, just to define everything one more time, I'm not going to say it. I'm just going to, I'm not going to write it. I'm just going to say it because almost all of these variables are the same. A is your total. So this piece right here is your total. P is your initial investment. Once again, that's your principal amount. 1 is 1. That's just a number. R is going to be your interest rate once again. T is the amount of years that you have, been doing this compound interest. So all of these variables are the same. The only one that is different is N. N is the amount of times that your interest is compounded per year. And that's always going to be defined in your question, or that's going to be the number that you're looking for, one or the other. Okay. So basically, compound interest, again, is you are putting in some amount, and then you're getting interest on it over the course of however many years this interest is accruing, and you're hitting that interest multiple times in a year. Okay, so let's say, and this is going to be your last classwork example here. I want you guys to use this formula that I have listed here, and I'm going to give you an example, which I'm not going to write it out because I'm just going to put it in your classwork. I'm just going to read it here. If the initial amount put into the bank was $100 with an interest rate of 4% over 6 years, what would the total be at the end of the 6-year period if your interest is accrued annually, if it's accrued semi-annually, and if it's accrued daily? So you have to do 3 different formulas here, okay? So I'll help you set up the annually one, and then we'll do, I'll leave the other 2 for you. So semi-annually and daily. If you're not sure what semi-annually means, that's synonymous with biannually, which means twice a year. Please don't confuse that with biennially. That means once every other year. So, once every 2 years. So semi-annually means twice a year. And then daily, of course, means daily. And don't assume that this is a leap year. Please just assume. I've had students ask me that in the past. This is just a normal year, so 365 days. Okay? Okay, so let's try to set up the annually one. We'll do that together here. Okay, so if I want this, if we're talking about annually, then what does this mean? This means, again, A is equal to 100, right? 100 is my starting amount, so 100 is my P. Then I have 1 plus, my interest rate is the same from the previous example with the simple interest. So my interest rate is going to be 0.04, and it's going to be divided by, well, how many times is this happening? Again, you know how many times it's happening per year because it says annually. So that means once per year. So divided by 1. And then I have, if it's happening annually for 6 years, I have 1 times 6 up there for my exponent. So simplifying this, I have A is equal to 100, and then I have 1.04 to the 6th power. And at this point, I would expect you guys to just plug this into a calculator. I already have the answer here. So the answer comes out to be 126.53. Okay, just round your answer for the next 2. Round your answer to the nearest 10th. I'm sorry, to the nearest 100th place. Because, if we're talking about money, we want to talk about, cents, right? So we get 126 and 53.53. So if this were, dollars, $126.53. Okay, so that's how we do this. That's how we set this up. You're essentially just taking your formula and you're plugging things into your formula. Okay, so I'll give you guys a couple seconds. Try to figure out semi-annually and also daily. Okay, and then the one thing that I want you to ask yourself here, and again, it's going to be included on your classwork assignment, so just read it there, but I want you to determine whether or not the amount is going down, going up, or remaining the same as your interest is accrued more often. And of course, you'll get that answer as you figure out what semi-annually and daily come out to. Okay, so let's go ahead and do these together. I'm actually not going to erase this because I want to keep this as a point of reference. So let's do semi-annually together now. So semi-annually, what does this come out to be? Again, we start with our formula. A is equal to our initial amount, which is still 100, and it's always going to be 100 in all of these cases. You're always going to be having 1 plus 0.04 on top, but this time our denominator is changing, right? Again, n, which coming over here, this is your n, right? Your denominator. N, and also part of your exponent, is going to be the amount of times that interest is accrued over the course of 1 year. So semi-annually tells you it's happening twice a year. So that means we're putting a 2 down here, and we're also having a 2 times 6, and 6 is, of course, still the amount of years that this is happening. So notice, all that's really changing between annually and semi-annually is our denominator of our fraction, and our exponent is changing. But all the other numbers are staying the same. So that should, give you a hint for what daily is going to look like. But in any event, we simplify this a little bit. So simplifying this, we get 100 times 1.02 to the 12th power. And once again, with a calculator, I can tell you this comes out to be 126.82, rounded to the 100th place. Okay, cool. And now let's go ahead and do what happens if you do this daily. So doing this daily, well, once again, we have A is equal to 100, 1 plus 0.04. None of this has changed, right? Your 100 is your principal, same as it always been. 1 plus is just part of your equation. 0.04 is your interest rate, which is still the same. And the only thing that's changing is now you have to ask yourself, okay, if this is happening daily, how many days are there in a year? And again, I told you guys no leap year, right? So no 366. There are 365 days in a year. So if it's happening daily, it's happening 365 times. And this is to the power of 365 times 6. I would never expect you guys to do this on a test. Do not fear. But still, while you're in the comforts of home and you have the luxury of calculators available to you, hopefully you can try this. You can figure out that this comes to 127.12. And now the question that I posed to you was to figure out, as this is happening, well, what's my amount doing? Is it going up, going down, remaining the same? How do I compare this to simple interest? Well, when we did simple interest, hopefully you guys have this in your notes, our amount came out to be 124, right? So I'm just going to draw up here. Simple came out to be 124 on the dot, right? As soon as we changed it to compound interest, even though it's only happening one time, it's only accruing one time per year annually, notice how our amount went up, right? We went from 124 to 126.53. Our number went up. So obviously, when we're doing compound interest, the amount that you get back, assuming your inputs are the same for simple interest as they are for compound interest. So what I mean by that is assuming it's happening for 6 years in both of them, assuming your initial investment is the same, so 100, and assuming that your interest rate is also the same. So assuming that all of those factors are the same, compound interest is always going to give you a higher number. Well, most of the time it's going to give you a higher number. Okay, so notice again, simple interest, we got 124, and just from switching it to compound interest, we got a higher number here. And what's actually going on? Well, we see the number's getting bigger. It's not substantially bigger, but it is getting larger as we accrue more often, right? So we accrued annually, so one time per year, we got 126.53. We accrued semi-annually, which means twice a year, and in doing it twice a year, we got 126.82, so the number did go up. And then when we do it daily, we have another increment. So now it's at a peak of 127.12. And you might be like, okay, well, is this really that big of a deal? Is this really, that important? Why do we care about how often this is accruing? And all of the big wealthy fat cats on Wall Street would laugh at you, because the entire idea behind this is that your initial investment and your interest rate play a very, very, very big part as far as the amount of interest that you get back, and hence the amount of return that you get back. So notice our interest rate isn't that great. It's 4%. That's, there have been better interest rates. And also, we're only starting with $100. That's it. It's $100. You can make $100 from like 2 days of work, right? So $100, you throw that into a bank with compound interest. After compounding, if you were to compound daily, well, cool. You have now made $27 as opposed to the $24 that you would have gotten if you threw this into a bank with simple interest with the same, exact variables. So the idea here is that with compound interest, assuming all of your variables are the same, so assuming your principal amount is the same, your interest rate is the same, and the amount of years that it's happening, compound interest should return a larger amount than simple interest. And also, as we see here with just happening between annually, semi-annually, and daily, well, the more times that you accrue, or the more times that your n is larger, so n, remember, controls your denominator and also part of your exponent. As n gets larger, we see that we get a larger return as well. Okay, so you might ask yourself, okay, well, we went from hitting it once per year to hitting it twice per year to hitting it 365 times a year. What happens if that number gets bigger and bigger? What happens if we do it twice a day instead of once a day? Or if we do it, once every hour? What happens if we do it once every second? And then so on and so forth. And that idea is the idea behind continuous compound interest. Continuous compound interest is the idea that you are compounding as literally as fast as you can towards infinity. Every single like nanosecond, and even faster than that you can possibly compound, you're doing it. And there is a formula that we'll talk about next time. I'm not going to hit on compound interest here, but I just wanted to touch on that idea. So again, the idea behind continuous compound interest is you're accruing faster and faster and faster, and there is a formula for that, and we'll talk about that next time. Okay, so I'm going to stop the video here. I've been recording for a little over an hour, and this should be good enough. Try your hand at the homework. Let me know if you encounter any questions, and of course, feel free to reach out to me for anything else. All right, guys, have a great night or morning whenever you're watching this, and I will talk to you next time.